All right, it's 2 minutes past 9. Let's get started. Good morning, good afternoon, good evening, everyone. Depends on where you are. Thank you for joining us as we start this MICCAI Fellow Talk series again. My name is Pinkun Yan. I'm a professor of biomedical engineering at Rensselaer Polytechnic Institute. It is my great pleasure to host this webinar together with my MICCAI board member colleague, Dr. Martina Giannato from Imperial College London. This webinar series highlights the work and insights of MICCAI Fellows. As you know, MICCAI Fellows are a small and distinguished group of MICCAI members who have made significant scientific contributions to the field, as well as dedicated service to the MICCAI Society. Today, we are super excited to have Dr. James G. from our MICCAI Fellow as our MICCAI Fellow speaker. Dr. G is a professor of radiologic science in radiology and in computer and information science at the University of Pennsylvania. His group carries out research in biological and medical image analysis and radiological AI. His team is best known for methods that have enabled population imaging studies, digital atlases, and computational anatomy. They are also recognized for their open source tools, which directly underpin hundreds of published imaging studies across the world every year. This research is complementary to his educational activities. He is involved in a lot of the training programs. A new research direction focuses on medical AI now for low resource environments and global health. Professor G was awarded a MICCAI Fellow in 2024 last year for the significant strides he has made in the field of medical imaging science through his pioneering development and open source distribution of computational methods. His work has democratized access to essential tools and resources, enabling researchers worldwide to build upon his innovations. Professor G's generosity in sharing these methods has accelerated research progress, fostered collaboration, and enhanced the overall quality of work within the field. His contributions are a testament to the importance of accessibility in advancing the scientific discovery. So without further ado, let's welcome Professor G for his talk.
All right, great. Let's see. Do you see my slides?
Yes, looks great.
Okay. Well, thank you so much, Benka, for the super kind introduction. I'm not sure I recognize the person that you that you spoke about, and thank you, Martina, and thank you, Diana, and everyone else at MICCAI who helped make this special speaking opportunity available to me today. And what I've planned today is for me to take a bit of a walk down memory lane instead of talking about our latest work. So just be a little bit different than what I'm used to, and I hope it works out. So I've been at Penn for more than 30 years now. I trained here before I joined the faculty, and I've learned a few things along the way about the institution that you may find interesting. So Penn is America's first university, founded in 1751 by Benjamin Franklin. At the time, there were colonial colleges, but these were concerned with training for the clergy. And what distinguished Franklin's vision was his focus on preparing students for lives of business and public service. And his proposed program of study would become the country's first modern liberal arts curriculum and really the template for American higher education. The spirit of innovation in education runs strong at Penn and includes establishment of the nation's first medical school, which is where I work. The university today is home to 24,000 full-time students, more than half of whom are pursuing graduate degrees. There are nearly 6,000 faculty with 2,900 in the tenure track. Penn's annual budget is about $16 billion and received over $1 billion in research funding during fiscal year 2023. As another indication of its size and impact, the university is the largest private employer in Philadelphia, which is the sixth largest city in the United States. The School of Medicine, the first in the country, as I mentioned earlier, was founded in 1765. The school has maintained its stature, consistently ranking among the top 5 in NIH funding. Another measure of its research excellence might be a Nobel Prize in Medicine, which was awarded in 2023 for work carried out at Penn that paved the way for the development of mRNA vaccines that ultimately helped the world turn the tide against the COVID pandemic. Penn is also the birthplace of technological invention, and we like to take credit for introducing ENIAC, the world's first electronic, large-scale general-purpose digital computer. And relevant to my presentation today, Penn has also ushered in a number of important new ideas in imaging, including the development of the first digital anatomy atlas of the human brain, as well as the first algorithms for elastically matching the atlas to medical imaging data. So shown here is my thesis advisor, Regina Baici, who is responsible for many of these remarkable innovations. These foundational developments cited by the National Academy of Medicine were preceded by another set of extraordinary events at Penn that revolutionized the imaging of human brain function. It was at the CVRC, the Cerebrovascular Research Center at Penn, that positron emission tomography, or PET's potential for quantifying regional cerebral function, such as blood flow and volume, was first established. The radiotracer fluorine-labeled deoxyglucose, FDG, developed by Martin Rivich and Abbas Olavi and co-workers, has been hailed as the, quote, molecule of the 20th century, unquote, for its unparalleled and unique impact on the evolution of the field of nuclear medicine. Well, the emergence of FDG PET presented new analysis challenges, and in particular, a method was needed that could anatomically localize the activation imaged in a PET scan. In other words, they had these incredible pictures for the first time of in vivo brain metabolic activity, but they needed to know where exactly in the brain this activity was taking place in order to fully make sense of what they were seeing and measuring. It's no different than, say, having a heat map of the newest pandemic cases in a country. The image or data becomes much more useful when we have more precise information about where exactly the hotspots are located, which state, which city, which county. To address this problem, Ruzhna, working with her student Hein Broy, leveraged the fact that, to a certain level of detail, the anatomy of normal individuals like you and me can be thought of as quantitative variations on a common underlying qualitative plane. In other words, we all share a common anatomical or bodily blueprint. So all of us here, I hope, I actually can't see you, but I hope you have 2 eyes, a nose, a rough symmetry midplane, and so on. At the same time, there are obviously differences among us. But we can think of these differences as representing variations on this shared blueprint. So my nose may be a little smaller or bigger than yours, my face may be rounder, and so on. Ruzhna proposed that a natural way of using this knowledge about human anatomy is to imagine that a given person's anatomy is a warped or deformed version of some template or reference anatomy. If this warping function could be calculated, anatomical features or structures can be identified just once in the reference anatomy and then automatically identified in an individual through the warping function. In developing what became to be known as elastic matching, Ruzhna and Hein formulated the problem of registering 2 images as one akin to the continuum mechanical process of physically manipulating and applying forces to an elastic solid version of an object depicted in one of the images so that its deformed configuration resembles the target object in the second image. These groundbreaking ideas, developed more than 40 years ago now, brought about a paradigm shift in medical image analysis from slice-by-slice 2-dimensional processing to fully 3-dimensional analysis, a paradigm shift that was a precursor to active contour and physics-based models that later became pervasive in the field. And here are those ideas implemented for the first time in code and applied to a very early computed tomography study of the brain in 1981. And here's a more contemporary version of the same application, this time using some of our latest image registration technology to help create the most detailed atlases to date of brain cell types across human and animal model systems. These types of very large-scale studies, in this instance of the brain, are made possible by the availability of computational pipelines that can now routinely provide detailed quantitative characterization of both structure and function in our multimodality imaging data. And here are some examples of one component of the pipeline in action across very different brain data sets. In particular, the images on the top row show the relative cortical thickness or gray matter thickness computed within each brain, with the thinnest regions indicated in blue and the thickest areas in red. The pipelines also need to handle very different brains within our human studies. And here we see the differences in cortical folding and thickness across human development, as well as in the pathological state, as shown in the very far right column, in this example due to frontotemporal degeneration. Now, these kinds of brain imaging measurements can also inform about behavior. And by way of example, shown here is a result we get by looking for which regions in the brain are most predictive of cognitive performance on various language tasks in a cohort of subjects with FTD, which is frontotemporal dementia, which is a neurodegenerative disorder that afflicts language processing among other types of impairment. And we do this by running a sparse regression that finds a linear combination of predictors, in this case, both brain gray and white matter regions, the best modeled language cognition evaluated in our tasks. And shown here are the selected regions for each of the tests. Pink to red regions are in gray matter, and blue regions are in white matter. It's evident, and this reinforces the importance of multimodality approaches, that white matter integrity plays a complementary role to cortical thickness, since white matter predictors, the regions shown here in blue, are consistently included, as we can see in the figures here. And here's an example of another model developed to identify how the brain of a, quote, average subject, unquote, with a specific condition might change over time. The average subject in this instance being identified by average age, education, and psychometrics for each gender, or whatever other information we might have. If we now change a variable, we're able to understand the impact on, for instance, the rate at which brain atrophies, as illustrated here. So in this study consisting of frontotemporal lobar dementia and Alzheimer's disease patients, increasing the variable education, for example, by 4 years decreases atrophy rate by 0.5% in our model. Now, while these studies help showcase our pipelines, they only involve many dozens of subjects. So the power of our automated processing is truly unleashed when it's applied to the tens or hundreds of thousands of data sets that are now being collected by many countries and organizations, including at my own home institution, to build population and medical biobanks based on the idea that every patient potentially constitutes a research subject and every visit to the clinic represents a data point. These biobanks are invaluable because there are a very large number of high-quality phenotypes that are obtained. And taking our own Penn Medicine Biobank as an example, we obtain diagnostic codes, ICD-9 codes, procedure codes. We get vitals, body mass index, blood pressure, weight, history of smoking, and medications. And we also obtain normal laboratory serum and biomarkers. There are many additional phenotypes, and one of these we've naturally focused on is medical imaging data. So just as before, but now at a much larger scale, we can study associations between disease and any imaging trait, such as, for example, liver fat as measured from abdominal CT scans in the study shown here. That's part of an ongoing research program to improve our understanding of nutrition that's led by my radiology colleague, Walter Witchy. This is an example of a PheWAS or phenome-wide association study. And the way to interpret this is similar to a genome-wide association study. Namely, that the y-axis here indicates the strength of the association between the imaging trait, here this is hepatic fat, and the x-axis indicates a certain type of disease, as indicated on the electronic health record, as represented by, for example, an ICD-9 or ICD-10 code. And what you see is first that it does what we might expect, that the largest associations with hepatic fat are diseases we'd anticipate. For example, chronic liver disease and cirrhosis, as well as other chronic non-alcoholic liver diseases and diabetes and so on. But what's most interesting and what really illustrates the utility and power of these types of PheWAS studies are the associations that are above the Bonferroni level of significance that's shown here by this blue dashed line at the bottom of the chart. Particular disease traits that are above this line show some association with hepatic fat, and some of these are unexpected. So diving deeper into this type of data will be extremely interesting in terms of uncovering patterns of disease that have either previously been unknown or understudied. Now, I didn't mention that in the preceding prediction task of language ability and brain atrophy that we relied on anatomically constrained matrix factorization techniques to obtain the regions of interest, or features, if you will, that were then used to encode the imaging data. Well, the field now is dominated by interest in neural nets, but we find over and over again that having possession of intimate domain knowledge consistently yields the most significant performance gains. And this is a general theme that runs throughout our work, and I believe is essential to realizing the potential of AI and automation in practice. So in the 2023 Algonauts Challenge shown here, the goal was to develop models that were able to predict brain responses while subjects looked at natural scenes. And here the animation is showing how the functional MRI response data is captured with a subject lying in a scanner with a screen setup. The participants are viewing images as they're being scanned. They also have a controller so they can press a button to answer questions. And this is what the challenge data looked like. Each image presented to the subject, that's shown on the left, is paired with a brain scan shown on the right. And in particular, only responses within the visual cortex were of interest in this challenge, and we've flattened this part of the cortex here just for presentation purposes. So the challenge represented a classic brain decoding task, and a winning solution significantly outpaced the international competition. And without getting into details, our model was handcrafted to mimic essential architectural elements of the human visual cortex. And my student, Jose Yang, deserves all the credit for this incredibly meticulous work. His model was extremely impressive in recapitulating known visual science. But even so, its performance leveled off at around the same score as the best competitors. So what boosted our effort to the significantly higher top score was hacking the challenge by taking into account additional specific knowledge that we had about the experimental setup. So instead of just simply or just using the provided images as the nominal input data, which is how the challenge was actually organized, we additionally took advantage of the fact that the images were presented in a sequence in the original fMRI experiment. So we included along with the nominal images its preceding images in a presentation sequence. We also knew that each image was presented to a participant multiple times in the experiment, and so we additionally labeled each image by the number of times they'd been presented before. And lastly, the scan sessions were in 5-minute blocks. And we know the brain keeps track of time, and indeed it appears this clock signal could be predicted by adding as another input to our model the specific time at which an image was presented during a scanning session. So an important point here is that a seemingly straightforward and very carefully designed task is confounded in practice by a great deal more complexity in the real world. And it may be imperative for us in many of our practical situations to have to understand and account for this complexity in our own applications. So I'd like to return now to the image processing pipelines that we had started out talking about, and in particular, the image registration component that is a workhorse of these pipelines. Among the advances since the invention of elastic matching, one of the most fundamental has been that our correspondence mappings are now optimized over diffeomorphisms. These are just a set of differentiable maps with differentiable inverse. In other words, the topology of the domain, in this case, the image that's being transformed or normalized, is maintained or preserved by the transformation mapping. And this is important because the diffeomorphic property exactly implements Regina Baici's original continuum assumption. And what's additionally exciting about this development is that it's led to a rigorous formulation of a distance or length metric defined over the transformations or diffeomorphisms. And what this translates to in practice is the availability of a yardstick or a ruler for anatomy that allows one to properly measure the distance between two instances of the same anatomy. Here, for example, the average brain configurations are compared between chimpanzees and humans in a collaboration with Tom Schoenemann, a physical anthropologist formerly at Penn and now at Indiana, who's interested in questions about human brain evolution that can potentially be informed by knowledge about how our brains differ from those of our closest ancestors. And in particular, brain region of special interest to Tom is the prefrontal cortex involved in planning complex behaviors. And our analysis confirmed that this region occupies a proportionately larger part of the brain of Homo sapiens than it does in pan-troglodytes or chimpanzees. Now, these diffeomorphic maps are traditionally generated by integrating a time-dependent vector field, and this is a velocity field, just a velocity field effectively over time, starting from X, the identity configuration. And the idea here is that by ensuring the velocity field is smooth, the displacement mappings we get by integrating the velocity field will themselves be differentially smooth. In other words, diffeomorphisms. There are two constraints on the optimization problem. The first constraint is that at time 1, the diffeomorphism should map image I, shown on the far left here, into the space of image J, shown on the far right. And the second constraint is that the length of phi, the mapping, should be as small as possible, and this length is described by the integral over time of the velocity field size. So by solving this problem with these constraints, in other words, by solving the registration problem, we can smoothly map image I into the space of image J, as shown here. Now, there is, however, a very serious shortcoming of the approach I've just presented, and in fact, with all conventional registration methods in general, and that's the fact that the formulation and the viewpoint it takes are fundamentally asymmetric. The path from image I to J and the opposite or inverse path from image J to image I are not the same. In other words, the metric distance between our endpoints, the total deformation summed in time, actually depends on which image we choose as a reference point. And what this means is that the direction in which a registration is performed actually makes a difference in practice. And this bias can clearly be a problem for the kinds of quantitative applications we're interested in for any of our imaging studies. Well, fortunately, there is a way to fix the problem, and to see this, the idea is again to generate the mapping phi in the same way as before as the integration of a velocity field, except what we do now is we move the endpoint condition to the middle of the path by explicitly representing the component of the diffeomorphic map that operates on image J. What this means is that the geodesics, or the shortest diffeomorphisms connecting the two images, are now required to be the same. And this now gives us a set of symmetric Euler-Lagrange equations that depend on gradients of both images I and J, as opposed to just image I in the original formulation, which is precisely the asymmetry that causes the bias in standard registration. So I think it's super helpful to take a look at the symmetric normalization in action, because the basic algorithm is so much easier to appreciate when we do so. So in particular, let's consider as shown here the sad face on the far left as image I, and the happy one in the middle as image J. I'm using smiley faces here only because it's again a whole lot easier to show the effect of the algorithm with these cartoon faces than, say, with real brain images. So note where conventionally one image is typically deformed into the other. Both images now deform into the mean configuration at time equal to 1/2, and the total symmetric normalization or path between the two images is obtained by composing the two diffeomorphisms shown here. So rather than going from sad to happy, I to j, or happy to sad, j to I, both cartoons first become sappy. All right, and this is supposed to get a laugh, but since I can't see any of you out there, you're probably all groaning instead. but, but, but in any case, to go from sad to happy, for example, you start with the depressed state, you flow into sappiness, and from there you take the inverse mapping from sappy to happy. The path from I to j is now identical to the path from j to I. And what's even better is that this symmetric registration not only gives us unbiased results critical to quantitative studies, but also results in significantly improved performance because all of the images now contribute to the calculation, as you heard earlier and as you can see annotated here, where the gradients are taken with respect to both images in the pairwise registration problem. And this performance gain has been essential in making practicable Regina's original elastic matching idea for automatically segmenting or identifying the anatomy depicted in biological and medical imagery. And the use of these anatomical postulations has become perhaps the most popular method for hypothesis-driven analysis of imaging data. State-of-the-art results shown here from our lab represent the efforts of a good number of people, in particular folk pictured here, Gary Zhang, Phil Cook, Jeff Duda, and Paul Yushkovich. Now, as a quick technical aside, a very convenient property of the symmetric normalization approach is that it naturally generalizes from pairs of images to define a symmetric population study of an arbitrary number of images. And an easy way to see this is to note that the pairwise symmetric normalization algorithm effectively solves the two-mean problem. We saw how we actually solve for the mean when going from I to j and j to I, and then transition with the mean configuration to get from I to j or j to I. Well, a population study simply corresponds to solution of an arbitrary n-mean problem, n being the number of subjects in the group analysis. And this is exactly what the generalization provides. It finds an optimal reference coordinate system or template I bar given directly by the n-mean configuration, which by definition minimizes the total length of the set of diffeomorphisms phi operating on a subject image's ji. And these diffeomorphisms are exactly the population normalizing transformations of interest to us in a group study. Well, here's one more extension that I'll again only briefly mention, but this was crucial to the construction of the cell atlases that I highlighted earlier. What's shown here in work carried out by one of my former PhD mentees, Gang Song, is the 3D reconstruction of a stack of two-dimensional Nissl sections into what ultimately became one of the original versions of the Allen mouse brain atlas that's a predecessor of the new generation of atlases being built at the Allen Institute today. The reconstruction is obtained by estimating a smooth approximation to the volume in the analogous way that one smoothly approximates a curve through a given set of points. Here, the approximated value is a deformed version of a given two-dimensional section I that minimizes the length of the mappings to its neighboring sections. In other words, the maps from section to section parameterize the volume, and the length of this parameterization, or the total deformation, measures how much discontinuity there is between sections. And so by minimizing the parameterization's length, we make the section-to-section deformation or deformable differences smaller, and this results in producing a more smooth change in anatomical shape within the final reconstructed volume. All of these ideas and much more are encoded in or enabled by our ANTS software package, which is a major community resource today that directly underpins hundreds of imaging studies around the world every year. Now, I did say at the beginning I wasn't going to talk about any new work today, but I do want to slip in a quick plug for our next generation advancements to ANTS called Fire ANTS that I'm extremely excited about, and is a beautiful work of my student, Rohit Jena. So we're certainly gratified by the impact of our work on the research community, as well as in advancing basic clinical and biomedical science. Our ultimate goal, however, is to be able to translate our efforts toward direct improvement of human health. And here I'm going to wrap up by highlighting some work carried out quite some time ago now, but work that remains deeply influential in our current efforts. This work, which received a good bit of press when it was first reported, takes on a clinical diagnostic task with the goals that any system should ideally work just as well for diseases that are uncommon. And this should be the case even if training cases are scarce for these rare diseases. After all, it's these types of diagnostically challenging studies when the most help might actually be welcome in practice by our clinicians. The system should also differentiate between a large number of diagnoses, and importantly, it should provide direct access to intermediate features or information used to obtain a diagnosis. And before I continue, I want to make sure I give credit for the work to, and all of it goes to Andreas Rauschecker and Jeff Rudy, both of whom were just amazing radiology residents at the time working with me on this effort, and who were really the leaders on every aspect of this work. And what Andreas and Jeff set out to do was to develop a system that tries to computationally model the distinct sequential steps that radiologists use for image interpretation. And the first step is to allow deep learning to do something that it's pretty good at, which is detecting image abnormalities. And this simulates the radiology trainee learning to recognize abnormalities through lots of examples. Then the system uses additional image processing with quantitative outputs to characterize the abnormalities into human interpretable concepts, such as, for example, location or signal intensity or enhancement. And this step is basically akin to a radiologist explicitly describing imaging features or findings that they see in the patient studies. Our system covers typical features that radiologists look for in the reading room and include in reports as a quote-unquote explanation for favoring certain pathologies over others. Finally, we take these extracted imaging features along with, importantly, clinical features, for example, age and sex and duration of symptoms, and we integrate these imaging and clinical features into a probabilistic differential diagnosis by using standard Bayesian inference, just like the radiologists correlating imaging features with certain diagnoses based on their own expert knowledge. The magic, if you will, in this step is our access to a considerable domain expertise. So to assign a probability to an event, for example, finding a certain feature such as a high signal and diffusion, given the presence of a specific disease, such as, for example, acute stroke, we base our probabilities on literature if it existed, and if literature didn't exist, then we relied on the best estimates of our neuroradiology experts. So although the first step of this process, image abnormality detection, is purely data-driven, the final diagnostic step is explicitly informed by domain expertise in the form of expert-derived conditional probabilities. This is important because a system extracting imaging features that probabilistically differentiate diagnoses of interest doesn't necessarily require any additional training data to derive the actual differential diagnosis. Instead, the need for training data can be replaced by expert knowledge about the probability of these image features given each diagnosis. And this ability to trade domain expertise for raw data, we believe remains a potential advantage over end-to-end deep learning methods when applied to diagnostics that may have to cover not just a broad range of diseases, but also diseases of variable prevalence, including diseases that may be rare. So let's go through an example scenario. Here's a 42-year-old with HIV presenting with confusion. How might we come up with a differential diagnosis? Well, first of all, we can identify the abnormal signal here and localize it to the thalamus and adjacent white matter. That's helpful, but how then do we distinguish this among all possible diseases that involve the same deep gray structures? Well, radiologists rely on the fact that different diseases are associated with different clinical and imaging features, which allows them to generate a differential diagnosis. So for example, here are diseases most commonly found in patients with a compromised immune system. And here are diseases that typically result in poor contrast and post-contrast enhancement. And highlighted here are diseases associated with restricted diffusion. So the point here is we can group diseases in different ways, and if you were to know the probabilities of observing these features associated with the different diseases, then assuming that you can extract those features from the images, there are simple statistical methods we can use to calculate the probability of each of these diseases for a particular case. So how then do we detect abnormal signal? Well, an example shown here, we have an acute left basal ganglia infarct. On T1, there's going to be a low signal, and on T2 and flare, there'll be high signal. And in order to detect and characterize this abnormal signal on our T1, T2, and flare images, we use the automated processing pipelines that I mentioned earlier to segment the deep gray brain regions and map these regions across all the imaging modalities typically seen in our standard clinical imaging workups. Then the percentage of voxels within each region with normally high or low signal identified relative to average gray matter signal. We set the signal thresholds using, again, expert knowledge as before, and update these with training data if they're available. And all of this allows for an automatic determination of which regions are involved, as well as the quantitative feature state for these regions, meaning in this particular example, whether the imaging signal was high or low or normal for each of the relevant modalities respectively. For our initial effort designed to support diagnosis of 35 possible diseases that tend to involve deep gray matter structures, we extracted 12.5 of these types of imaging-related features that radiologists typically look for, as shown here. And all of these features, as well as importantly clinical variables, are then used to perform a lookup in a table encoding the probability for every feature state of every imaging clinical feature conditioned on the presence of specific disease included in the system. We use naive Bayesian inference to produce the final likelihood or posterior probability for each disease. And these probabilities are then compared with each other to come up with ranking of disease likelihood, much in the same way that a radiologist would put together a differential diagnosis. So how well does all this work? To find out, we compared a prototype system against radiologists with various levels of training, looking at the same 192 clinically validated cases hung in our radiology PAC system, anonymized with the exact same clinical information. So first, keep in mind that many of the cases were quite challenging. The 4 residents we tested generated a correct differential diagnosis for 55% of cases, which was similar to the 2 community radiology attendings at 52%, and these are individuals who read general radiology, including brain MRIs. Our 2 neuroradiology fellows were correct for 72% of cases, while the 2 academic neuroradiology attendings, whose results effectively serve as the ceiling performance that one might obtain here, got 85% of cases correct. The automated system, on the other hand, was correct on 76% of cases, which was significantly better than residents and community attendings, and on par with our fellows. Now, this final green bar shows how well the Bayesian network does in generating a differential diagnosis, when instead of using the automatically generated imaging features, we use the findings of features determined by our neuroradiology attendings as input into the model. And what's interesting is we see that the model was actually better than the attendings in correlating imaging features with certain diagnoses to create a differential diagnosis. And another interesting finding is shown here in this chart, which demonstrates the performance of radiologists and the automated system as a function of how common the disease is. Unlike radiologists who consistently perform better for more common diseases, the system's performance was similar across different prevalence levels of disease. Now, as encouraging as these very early results were from our team, as well as from many others in terms of demonstrating the medical potential of AI, the translation to the clinic, as many of you know, remains an open and vexing challenge to the field. One area in radiology, though, that seems poised for advancement is report generation. And this was the case even many years ago when we first built our system. At Penn, we use PowerScribe as our software for radiology reports. And you can imagine from what I've told you today, we can populate the finding section of the report using the output of image processing steps, and the impression can be populated by the system's probabilistic differential diagnosis. And this is exactly the scenario envisioned by the American College of Radiology in its effort to help advance the clinical adoption of medical imaging AI, where even though the diagnosis of pneumothorax, as in this particular use case example shown here, is by itself important, we get the greatest value when the diagnosis is additionally supported by information about relevant clinically interpretable imaging features, something that is a challenge for end-to-end black box systems. And there are many other potential advantages as well, including the fact that the findings section can now be tailored to particular diagnosis that it predicts, as well as to the audience receiving the report. For example, a patient might get one version while a different version is sent to, say, a neurosurgeon or primary care provider. The report can be tailored even to a particular reporting radiologist to include the information that that particular radiologist may wish to include. So basically, all the advantages of structured reports would be available to us here. And all of this quantitative data that we're collecting on eScan would also be very useful for data mining. It can be stored and then later mined if you're trying to learn something new about particular diseases, just as I highlighted earlier with our biobank studies. And finally, there are also teaching applications. And here's an educational tool we helped to develop and was being commercialized by former department chair Nick Bryan. This tool goes a step further and uses the diagnostic infrastructure we designed to allow trainees the ability to interactively manipulate imaging and clinical features and see in real time the disease probabilities as they're updated online. In his editorial accompanying the report of our brain MR diagnostic system in the journal Radiology, Greg Zaharchuk, a very senior radiology scientist in the field, was very generous, noting that a study was a quote-unquote impressive feat, but he also presciently pointed out that the work only represented a point on the journey rather than the destination. He echoed the many limitations we've highlighted ourselves about the work, but he was ultimately won over by the thought process behind our AI system. It mimics the way radiologists actually look at a study, starting by identifying the features on the image, integrating the clinical context, and then applying their training and experience to judge and rank the likelihood of disease. The system gives direct insight into the decision process by reporting the features, and in this way allowing the AI model to quote-unquote explain its rankings, which we can subsequently analyze to decide if they're plausible. The editorial concludes by applauding, quote, the incredible amount of work that went into designing the AI system and its good performance on a narrow task, but it also wondered aloud about, quote, how long the road ahead is before such a tool would be a must-have in the reading room, given the huge number of diseases that radiologists have to recognize in their work. And in suggesting this work charts a plausible way forward, Greg quotes Winston Churchill, who said, quote, now this is not the end, it's not even the beginning of the end, but it is perhaps the end of the beginning, end quote. So Dr. Saharchuk is definitely one of the smartest guys you'll ever meet, but I'm pretty darn sure he wasn't foretelling at the time the advent of large language models. These models, including some of our own recent work, open an even more promising avenue toward interpretable and explainable diagnostics. And I very much hope perhaps to be able to return and continue this fascinating narrative with everyone here. So let me close by inviting those of you who may have an interest to take a look at our lab's freely available software resources, as well as others to which we contribute that implement many of the results that I presented today. And finally, I'd like to acknowledge all of our current and former lab members and collaborators who I've had the incredibly good fortune and pleasure to work with, and who together are the people really responsible for and who deserve all the credit for everything you've heard me talk about today, and a whole lot more. They're far too numerous to name, except for one special individual who has had an outsized influence on our work. And that's Murray Grossman, who founded the Penn Frontotemporal Degeneration Center. Murray and I were each other's longest collaborators. We met at Penn when I was still just a trainee, and we went on to forge a decades-long partnership during which the research at his center provided the biological and clinical impetus that drove many of the technical innovations for which our lab has become well known for. Murray's recent passing is an incredible loss, not only for the field, but for the patients and families all over the world that he and the FDD Center served. I wish to dedicate this talk to my friend and collaborator, Murray Grossman. I'd like to end by highlighting that Murray, along with many of our other amazing collaborators, as well as many of our even more amazing lab members, are foreign-born, like myself. Also, all of the work I presented today was supported in part by the NIH, a government funding that is now in real peril. There have been rallies and events held all across the country here in the United States, and I encourage you to show your support wherever you live, to defend academic freedom, to defend science, and to ensure that foreign trainees continue to be welcome in this country, as well as to ensure that all of our amazing trainees all around the world have a bright future to look forward to in research and in science. Thank you very much again for the opportunity to tell you some of our lab's work, and hopefully some of what I talked about today was interesting to you. Thanks so much again.
Thank you so much, James, for the excellent presentation. Do we have any questions for James? You can write your questions on the Q&A, and then we can read them to James.
So James, while others actually are thinking about their questions, I have one. So you mentioned that we're right now probably at the end of the beginning. So what do you see the next like 5 to 10 years that the research field is moving towards, especially on the multi-model data analysis?
Yeah, so I don't have a crystal ball in front of me, but I wouldn't be surprised if we see more and more deep learning and machine learning and models, vision language models and large language models. I also expect to see actually a lot more theoretical development. We are. It's crazy to believe that we're already in sort of maybe a teenage phase, a middle age phase of deep learning, where there's still a lot of applications that keep the field busy in medical imaging in particular. But we're certainly seeing many of our colleagues now focusing on spending a lot more time thinking about their theoretical underpinnings of this work. Which at the end of the day is going to be so critical in terms of advancing both our methodology and our applications. It's difficult to debug things if you actually don't understand how they work. It's also difficult to trust them if you don't truly understand how they work. We happen to work in a very high stakes environment, and so I mentioned that uptake in the clinic is still low. As always, it's a very conservative discipline that we work in, and rightly so. And I, for one, would be hesitant, to use anything that we don't fully understand. And in particular, if it stopped working. The challenge, of course, is that these methods do work so well most of the time, and it is very easily to be seduced by the fact that they work so well most of the time. The concern is when there is catastrophic failure and what do you do about it. Another challenge, Pinkang, that you brought up is that, it's interesting that we highlighted sort of the open source work that we do as being a benefit to the community and to society. And indeed, that's been one of the major advancements in the field not just in medical image computing, but just computing in general in terms of the proliferation of publicly available tools that allow, as you said, democratizes the access of very powerful techniques to folk who have very little computer science training or background to be able to write code. They can talk to ChatGPT, and ChatGPT will generate code for them that they can literally run. At the same time, we all know that it's incredibly dangerous to put such powerful tools in the hands of folk that are unexperienced. So I don't want to oversell the point, but yeah, it's kind of like putting a chainsaw in the hands of a of a 5-year-old, and if they're able to cut through a block of wood without hurting themselves, then okay, great. But they can also potentially do a lot of damage, not only to the block of wood or to the house in which they're using the chainsaw, but also to themselves. Again, I don't want to belabor the point, but we are running into this problem. Certainly, Pinkeng, you and Martina, all of us as educators, we are now beginning to struggle with the fact that there are all these tools out there, and how do we integrate these in terms of how we train and make sure that our trainees are properly trained to use these as resources as opposed to crutches, or as opposed to ways that are potentially harmful even. And anyway, that's a little bit of blabbing from an old timer.
Thank you so much, James. Yeah, that's a great insights. Yeah, wonderful. So I think that also integrates very well with your role as the educator, right? You train a lot of people, the fellows, the students, etc. I think that's a shared responsibility for all of us, to be responsible in the education and also training the next generation of the workforce, especially with the AI machine learning. Thank you.
Great. James, we have questions from the audience.
Okay.
So one question is, can the framework you described accommodate piecewise smooth transformations for registration?
Yeah, absolutely. So this goes way back, it's a great question from the audience. And in fact, lots of times we get the questions like, why differomorphisms in the first place? Why are the registration folk so hung up with these class of transformations? So hopefully the little history lesson here, dating back to sort of like the original continuum assumption, is sort of like why differomorphisms are interesting. The whole purpose of it originally, to map atlases, is this idea that we wanted these mappings, in fact, to be continuum mappings, and so that the labels would transport correctly. But as everybody knows, there's almost no, I kept pointing out that in the real world, things are a lot more complicated. And indeed, there's almost no registration problem unless it's sort of an inter-individual longitudinal studies where this assumption of this diffeomorphic sort of property actually holds in practice. And so you want to introduce discontinuities. And so one way would be through piecewise continuous. So you allow discontinuities along edges, and then the pieces themselves can be diffeomorphic. Lots of work has been done in the computer vision community that have looked at these, and they are perfectly well suited. They're perfectly, I should say, compatible with the framework that I've described. In this case, there'll be piecewise diffeomorphic, and the idea is that the regularizer term now gets a little bit more complicated. Some of the very earliest work, if you want to look it up, is Dimitri Tzopoulos' work in controlled continuity stabilizers or regularizers, where you actually not just only estimate the correspondence mapping, but in terms of optimizing the objective function, you also estimate where the discontinuities are in the mapping. And if you pick the right ones, the objective function again is optimized. So yeah, that is definitely compatible. And I encourage people to look up some of the historical work. That's another thing about training. Our trainees don't study any of the earlier computer vision work anymore, and it's our job to try to remind them that there were a lot of really good ideas back then as well. Thanks, Martina.
Perfect. We have one more question.
Sure.
Thank you for the insightful talk. I really enjoyed that you spoke about the integration of clinical with imaging data to utilize a more holistic image of a patient. However, a physician is privy to information they can directly ask the patient, which may not be accessible on a patient chart. How do you see AI methods evolving around this obstacle to better reflect how physicians work? Or do you see physicians and AI working together in this aspect?
Yeah, so those are fantastic questions, and I'm not sure if I feel qualified to answer these questions, but I can speak of work that's going on in the field, and even at my home institution, where we have a project where we have a clinic of the future, if you will, and we're not the only ones who are doing this, where we have a room outfitted with sensors that is in real time recording the interaction between the clinician and the patient. Currently, the project is actually just collecting data to build out a vision language model and other models that can take in this interactive component in addition to the other components that I had talked about, and try to have that then inform future patient encounters. So I agree that this is incredibly exciting, and I think is another way in which the field is hopefully going to advance and improve sort of the clinician-patient encounter, which I know for many of you, and certainly for me, the current methods in terms of which, at least in the United States, typically if you see a clinician, they're actually sitting by the terminal and they're staring at their terminal because they're entering their dialogue with you, and they actually don't look at you, and you're speaking with them as they're asking questions. Of course, every now and then they do turn around and they do a physical exam as well. But we do appreciate that the current mode of interaction is certainly suboptimal. And there are opportunities to leverage the interaction itself to improve healthcare delivery. This is something that I hope our field gets more into. We've been MICCAI, has been heavily focused on the image processing and image analysis component itself. And then the CHI component obviously is focused on the clinical environment within the surgical suite. There seems to be room for, as the person asking a question, to have yet another application, which is actually now, instead of looking at the surgical suite, look in the doctor's office at patient encounters, in addition to surgical processes. And I think that all the things that we're learning in surgical science would be very applicable, even in ordinary patient encounters. So all of the video techniques that are being developed in that domain would be incredibly useful, and I think would directly transfer in this particular application. So I'd love to see more of that at future editions of MICCAI, and who knows, maybe next year in Abu Dhabi.
Fantastic. One more question. Thank you for the good presentation. It was really insightful. Given the strategy you've shown, what is your opinion on this hybrid approach? Specifically, what do you see as the main advantages of leveraging deep learning as a black box only for the complex perceptual work, like feature extraction, and then deliberately keeping the final diagnostic reasoning inside a fully interpretable white box, like a Bayesian network?
Yeah, so these hybrid approaches are certainly attractive right now, just because they do offer an answer to some of the constraints and limitations that we deal with. I mentioned rare diseases, where by definition, there's very limited data. And many of these data-driven techniques, work extremely well when you have a lot of data. But what happens when you don't? And unfortunately, again, I talk about the real world. The real world is actually full of, small data problems. We get very excited about big data stuff, but and a lot of the examples that we show leverage the fact that those applications have quote unquote big data. We don't want to ignore the majority of applications that we have to actually address, which, like I said, fall into small data regime. And right now, it seems like hybrid techniques offer an immediate solution to this. Are there, is this the end all be all in terms of these applications? I certainly have been around long enough to never say never, and I can imagine. I can certainly imagine and anticipate some very clever folk being able to do, small data driven learning techniques. And again, I think a lot of this really is going to rely on the output of our colleagues who are working on the theoretical ends of things to help us understand sort of like what the Shannon's theorem is for deep learning, to let us know sort of like what are the sampling limits, what are these sorts of things that we know in other domains that will help guide us in terms of in machine learning, so that we have some better idea now, or have some idea at all in terms of like how to sample. So we have no idea how to sample, and in fact we don't. We just take whatever's available to us, right? And but in much more mature disciplines, they actually study that. They actually study. We just don't take whatever samples, and in fact we design our acquisition systems to sample intelligently. We don't have that luxury right now yet, and I think a lot of that has to do with the fact that we just don't understand what we don't fully understand what we're doing, and I think that's something that I personally look forward to, and I think will lead to completely new ways of doing things once we do that kind of thing. And yeah.
All right. Yeah. Thank you so much, James. Time goes by very quickly.
Yeah.
Several minutes over now, and it's time to conclude this wonderful session. So all the audience, please join me thanking our speaker again for the wonderful talk. Also, thank you everyone for joining us today, and for the thoughtful questions and discussion, make the session really meaningful. We look forward to seeing you again in our upcoming talks. Please stay tuned for the announcements. Hope to see you next time. All right, thanks, Jim.
Thank you, James.
Thank you, Martina.
Bye, everyone.
Thanks
Bye-bye.
again.
Everyone.
Thanks,
Bye.
everyone.